chemistry time.
No, theme song.
Chemistry time. Let's today we're going to talk about, mostly we're going to be talking about the gas laws, but we're also going to be talking about gas stoichiometry. The first thing we're going to do is we're going to have our, I'm trying to think of an adjective to describe you, illustrious chemistry students tell us how to solve the problems on the board. So the problem reads, calculate the change in volume of a gas as the pressure on it changes from 1.2 atmospheres to 0.99 atmospheres. The initial volume of the gas is 4.3 liters. We're assuming here that what stays the same?
The temperature.
The temperature. The temperature stays the same. It didn't mention that it changed. It's not really a very safe assumption, but it didn't mention that it changed, and we can't do it if it didn't, so we just assume that it did. What's the first step, Natalie?
We write down the equation.
Which is what?
P1 times V1 equals P2 times V2.
P1 times V1 equals P2 times V2. Next step, substitute, right?
No, you manipulate.
Yeah, no, we never ever substitute. We always have to manipulate before we substitute in these ones. Aisha, how should my substitution look? I don't mean that. How should my manipulation look?
You would divide over P2.
Yep, so we end up with P1 V1 over P2 equals V2. Now we can substitute. Correctly substituted in, Hayes is
1.2.
Whoop.
Oh,
You're-
1.2 atmosphere.
Yes.
Is 4.3 liters over 0.99 atmosphere.
Okay. Answer?
It's 5.2 liters.
There's a fourth step here. The solution is the third step, 5.2 liters. The fourth step is what? What should we do once we have our answer?
Substitute check.
You could. That would be a mathematical way. I was just going to recommend doing a conceptual check. This says that the pressure did what? The pressure exerted on the gas did what? It changed, but specifically how?
From 1.2
Wait, down.
Yeah, from 1.2 atmospheres to 0.9 atmospheres, which is a decrease in pressure. What, conceptually, what should happen as we decrease the pressure on a gas? The volume should increase. And did that happen? We went from 4.3 liters to 5.2 liters. This conceptually checks out. Another thing we kind of conceptually check for is if our answer is 107,000, we would be like, oh, this is probably right. It's a mathematical calculation error. They need to all be within the same, well, that is, the volumes need to be probably within the same order of magnitude, and the pressures need to be within the same order of magnitude. There are obviously exceptions to that, but if you're getting some outlandish answer, you might check your math work. Okay, the next one reads, calculate the change in volume of the same gas if its pressure stays the same, but the temperature instead is changed from 25.0 degrees Celsius to 0.00 degrees Celsius. Now what do? Kylie?
You write your equation. V1
You could do that first. Sure, let's do it.
over T1 equals V2 over T2. Manipulate it to equal V2 by multiplying T2 over.
By the way, it wasn't important in this one, but if we're trying to solve for either temperature, what should we do first when we manipulate?
You should change the temperatures
Well,
into Kelvin.
yeah, we're going to do that as a thing. That's not what I'm talking about. If we're looking at this equation, if we're solving for T1 or T2, what do I need to do first in my manipulation? Can we solve if it's on the bottom?
No, multiply it over.
Yeah, whatever I'm going for. Like, for instance, if I'm solving for T2, that needs to be in the numerator first. It'll make it so much easier. So first, even though we're solving for T2, multiply T2 over so it's in the numerator, and then divide the rest. We'll talk about that in a second. But then we always have to, as Tyler says, if we're working with any temperature that isn't Kelvin, we need to convert to Kelvin. So let's show that.
25 degrees Celsius equals 298.15 Kelvin.
Okay.
And 0 degrees Celsius equals 273.15 Kelvin. Now you substitute.
Okay.
T2, just 273.15 kelvins, times 4.3 liters.
Which we got from the last problem.
Yep, divided by 298.15 kelvins equals 3.9 liters.
Okay, now once again, if there's a certain volume of gas and the pressure or the temperature did what?
Decrease.
Decrease. So what should the volume have done?
Decrease. decreased.
decreased. And in this case, it went from 4.3 to 3.9, so that is what we found to be correct. Questions about how to solve these? There are two other laws. Gay-Lussac's law, which relates pressure and temperature, and then the combined gas law, which is all. Okay? So make sure you can manipulate and substitute and solve all of these simple, what I call simple gas law calculations. The next one we're going to do is the ideal gas law. So we're going to talk about that, and then we're going to talk about gas stoichiometry. And both of these things are really quite easy. In fact, there are many who think that the ideal gas law is an easier way to solve these. So let's talk about that real quick. First of all, we write this down. Ideal gas law. Let's just write the dang law first. That's a good place to start. PV equals nRT. Capital P, capital V equals lowercase n, capital R, capital T. Get out of here. You're too tempting.
Ouch.
I meant to do that. I'm good at angles. Okay, PV equals nRT. Like we always with our equations, except for the last ones, we're going to talk about what each of these things stands for. P is
Pressure.
pressure, measured in,
Atmospheres.
oh yeah, lots of stuff. Atmospheres, millimeters of mercury, torr,
But you always
bar.
put it in atmospheres.
Yeah, atmospheres is usually the easiest, and it's the easiest to comprehend. PSI, it could be, there are lots of standard units of pressure, but any of them is fine, as long as we know the conversion factor. V is, capital V is, volume, usually measured in liters, but it could be other things. You might sometimes see it in cubic meters, or if you're trying to make me throw up, you might see it in gallons, but usually
Gallons.
liters. Sometimes, quite frequently, actually milliliters will be used too, but liters is standard. N is amount. How do we measure the amount of a substance? I feel like you should know this. In fact, I know you should know this.
Amount of a substance?
Yeah, how do you measure the amount of a substance?
Like teaspoon?
Volume is one way to measure how much we've got, but that's not really amount. It can vary, as we saw in this. Volume can vary, but the amount of the stuff, what determines how much stuff there is?
Mass.
Mass is another way we could do it, but that can, I mean, that doesn't change quite as, doesn't really change, but this is not mass. There's another way we measure amount.
It just tells you. There's
Gram?
this much.
That's mass. Yeah, but it tells you there's this much, what are we measuring? What's the truest thing about how much stuff there is? Yeah, what's the truest thing we could measure about how much matter there is?
Weight.
No, that's even less true than this.
Weight.
I have no idea.
What is this?
So it's with an N, and it's a unit, or have you heard?
Milliliters.
Moles. We measure N in moles. That's how much stuff there is. Remember, 1 mole means there are a certain number of particles, and that's the amount of that stuff that there is. R is what we call is the universal gas constant. And there's a table in your book, and there's tables online. If you type in universal gas constant, it'll give you all the information you need. But not only does this have a certain unit, which varies depending on what pressure unit you want to use and what volume unit you want to use, but it also has a certain value based on those things. So for instance, your book, turn to page, I think it's, what do I remember? You can also find this on my what page evaluation.
454.
454. Tell me the first one there that's in, is the first one in atmospheres?
Liters times atmospheres.
Per mole Kelvin, yeah. But what is the number?
0.0821.
So not only do we have a set unit, but for this unit, which we're choosing atmosphere as our pressure unit, 0.0821 has a value, 0.0821 liter atmospheres per mole Kelvin. And then T, of course, is capital T is
Temperature.
temperature, measured always in,
Kelvins.
not Kevin's, but Kelvins.
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 What the heck?
What in tarnation?
You like my drawing? It's messed up.
Yeah, are you taking notes?
Mhm.
Oh, okay, good. Are you?
Yeah, we have this down.
Oh, okay, good. So for instance, I might know the amount of something. Let's say I have 1 mole, this is just an example of 1 mole, but if I have 1.2 0.13 mole of chlorine gas at 235 Kelvin and a pressure of 0.56 atmospheres, what volume does it occupy? What should I do first?
I found the equation.
What is the equation?
Are we dealing with all three? Dealing with all three? Yes. So the
No, you're making a mistake. Don't make a mistake.
it's
What
the
equation should I
volume
use?
Charles, volume and temperature.
Ideal gas law. So we're telling me what's right. Memorize that, please. Next step.
You substitute, or are we gonna have to manipulate?
You always have to manipulate, because once again, this is going to be two things set equal to three things, so we always have to manipulate. We can only do this if we have one thing on our side of the equation. So P equals nRT, what should I do next? Everything by P. So we end up with V equals nRT over P. Next,
Substitute.
tell me what's right.
So you're gonna have N, which is
So V equals,
1.1
oh, so close.
of C.
Yeah, make sure you have your, what the substance is with it, because that's going to be very important for the next thing, which is gas stoichiometry. But 1.13 moles of chlorine, that's my R. Which R am I going to use? How do you help?
Isn't it the
liters times
What is it? All the ones you're given are liters. It does exist in others.
18
So how do I know if I'm going to use this or 8.14 from your book? Or there are three different ones your book gives you. How do I know which one to use?
by what's being multiplied, right?
So look at the unit.
atmospheres?
Yeah, and so in this case, what is our atmosphere, or what is our pressure given in the problem? Atmosphere. So we need to use which R value?
0.0821.
Yep. 0.0821. Make sure you put your units with this, because this will tell you if it cancels out or not. Liters, atmospheres per mole Kelvin.
Liters, atmospheres.
Oh, and then I ran out of room, but what else? This should be multiply that by T, which here is 235 Kelvin. Don't draw yours sideways, I just ran out of room. 235 Kelvin. Oh, and by the way, is it degrees Kelvin? Shouldn't I be writing degrees Kelvin? No,
No.
it's just Kelvin.
It's
The
not
degrees
degrees.
that's in degrees Celsius and degrees Fahrenheit means it's that distance away from some nominal zero value. But in Kelvin, the zero is absolute zero, so you don't write degrees. Anyway, and then the P, pressure here was
0.56 atmospheres.
Yep, and now check out what happens with our units.
They cross out.
Yeah, do atmospheres cancel out?
Yes.
Yep, because it's on the bottom here and it's on the top on this one. Do kelvins cancel out?
Yeah.
Yep, because kelvins is on the bottom in this equation and it's on the top
Your
of this one.
moles
And then
cancel
moles
out.
cancel out because moles is on the bottom.
So you're
We're left with
Liters.
liters. And this volume generally measured in liters?
Yeah, that's
Yeah, of course it is. So now plug and chug. That means plug in your calculator and chug along. Plug and chug!
Oh,
Oh, sorry. Let me go whisper into the microphone. Plug and chug. That'll be great.
ASMR.
Moisten my lips first. Make a nice lip moistening sound.
ASMR with Mr.
Yeah, exactly. There we go. We got some.
Is it 38.9?
I don't
Wait,
know.
you have to
Someone needs to
wait.
corroborate.
38.9 is what I got.
But you haven't said it right yet.
Liters.
You got 38.9 liters.
He's still doing
Doesn't someone else bring a calculator to class with
You
me?
like my
it. Yeah,
abstract?
I did. It's right here.
Mr. Kind.
Okay.
Yeah.
38.9. Check your sig figs. Is that the right number of sig figs?
Yes, because the
Is it?
1.3 is 3, and that's the
Is
same
it?
one, and 0.56.
It's not. Why? What should it be?
0.0.
I have a scab on my knee from
Should just be
Thanks, man.
38 or
No,
39?
39. We round it. It should just be 2 sig figs because our pressure only had 2 sig figs. So
After that,
39,
you don't count.
39 liters is the correct answer. That's how we use PV. Any questions about how we solve an equation with PV equals nRT? So how are we going to tell if we need to use the gas laws or the ideal gas law? What's the main difference between them?
It has a mole in it.
The equation. Very good, Natalie. No. Okay, that's one way. If we're given moles, that might help us. But we're going to find out pretty soon that gas stoichiometry is going to make us use moles with the other thing too. What's the primary difference? In these ones, the questions were, well, how are the questions different in this bad boy to this bad boy? What are these moles
it has
involved?
a-
To calculate the change.
Exactly. Thank you, Aisha. The combined gas law, Guy-Lussac's law, Charles' law, they will always involve a change in something, from one thing to another, from one state to another. I don't mean state of matter, but from one situation to another. Whereas this is just calculating how it be in this one situation. Write that down someplace. Right now. I should get a gavel.
Please don't.
The combined gas law and the simple gas laws always involve a change in situation.
Combined law and what?
The gas laws always involve a
Combined
change.
law and what?
The combined gas law and the gas laws always involve a change in situation. I got you, Natalie. Whereas the ideal gas law is only involving one circumstance, one situation.
The combined gas law and gas law.
All about that change.
Show a change.
Yep. And the ideal gas law is about a certain set of circumstances at one.
This is a cloud of knowledge.
Label the cloud of knowledge. Okay, we're going to move on to talk about gas stoichiometry. The first thing we can talk about for gas stoichiometry is something
Is this
called...
whole lesson just math?
Oh yeah. Oh, chemistry is just math. You've been here for several months, girl. Write this down first. STP stands for standard temperature and pressure. Write that down, please.
We already have this written down.
Okay, fine, but you write it down again.
STP.
STP.
Standard temperature and pressure.
Standard temperature and pressure. And these are defined as 1.00 infinite zeros atmosphere of pressure and 273.15 infinite zeros Kelvin temperature. This is important because always, for any gas, well, there's some, for a perfect gas, that means a gas that is made of atoms that only have perfectly elastic collisions, that only bounce and never interact or anything other than bouncing. For a perfect gas, in a perfect gas, at STP, 1.0000 infinite zeros mole of gas equals 22.4000 infinite zeros liter of that same gas.
Wait, say that again?
We can use this conversion factor. 1 mole of gas is equal to 22.4 liters of gas.
Gas
And these have infinite significant figures.
is equal to 2.2.4.
No.
Gas.
Not 2.2.4, but just 22.4 liters.
22.4.
22.4 liters of gas. So 1 mole of gas is equal to 22.4 liters. Why is this powerful? It's a what? This is basically a, or an. What is
A
this?
conversion.
Yeah, this is a unit conversion. So as long as our conditions are at STP, we can use this as a unit conversion. And this is so powerful because now, instead of just being able to go from moles to grams or grams to moles or moles to particles or particles to moles, we can now also have volume. So I can say if I've got 1 liter, if I've got a 1 liter balloon of oxygen, and I react that with 1 liter of methane, we can do that stoichiometry, even though we only got them in volumes. So let's use an example. At STP, 26.93 liters of chlorine dioxide react.
Else other than chlorine.
Oh, okay. Fluorine dioxide, difluorine dioxide, which is sometimes called FOOF, which is terribly dangerous. Anyway, 26.93 liters of FOOF
Why is it dangerous?
react with. Oh, it's super poisonous and it'll start everything on fire. Just be careful with it.
Do you have it?
Oh yeah, I just carry it around in my pocket so I can start fire. No.
Do you
Anyway,
have
at STP, no, you can't even make it. 26.93, you can, but we're not going to. 26.93 liters of difluorine dioxide react with, let's just say sugar, and excess of sugar,
Which is C6.
glucose sugar, we'll specify glucose sugar, which is C6H12O6. To produce, help me, what is this definitely going to produce?
Water. Energy.
Water, carbon dioxide, probably some hydrogen fluoride. Oops, I spelled the word
We
produce.
can go try it.
Find the amount of carbon dioxide produced. What do I need to do first? This has all the information you need to solve it. What do I need to do first?
We're trying to find the amount of CO2, so we have to use that.
What's step one in the stoichiometry? I'm going to kind of switch gears a little bit here.
Oh,
You
molar
haven't done
mass.
stoichiometry for
Well, yeah, like 2 weeks, but
Molar mass.
we could do molar mass first. Generally, it's a better idea to start with what?
your, write it out.
Yeah, and you mean
Like your conversions.
yeah, but I think you're on the right track, but not the conversions. You're right.
The
What?
conversion bar.
No.
Like the.
How are we gonna know
all
what's
over your board.
what's the most important? What's the most important part of this stoichiometry problem?
The ratio.
The mole ratio. How are we gonna get the mole ratio?
Oh, we need to, you get what I'm saying.
Yeah, I
Balance
do.
equation.
Balance the equation. So we got to write the equation first. So we have foof plus.
Don't say foof.
Don't say foof. Plus that yields H2O, CO2, and hydrogen fluoride. So we have to balance this. Check it out. I think that does something. Well, this is actually going to be a double the balance. 5. I should have made one that wasn't a double the balance.
F
Is it even balanceable?
2O2 plus
Now you have 12 oxygen.
C6H12O6
I wish I didn't choose one that was a double the balance.
2O6CO2
Frick.
plus 2.
Technical error. Okay, well, we definitely didn't change anything here, but now we're going to resume the video. The first step, as we said, was to write down the equation. In this case, the equation, which has been the equation all the way along, and did not change at all because no one made any terrible mistakes, and no one here is stupid. Anyway, we're all very smart. We know what we're doing. The first step is what, Natalie?
You have to balance it.
And in order to balance it, I need to first
Right, your
write equation. So if I have hydrogen gas reacting with an excess of oxygen gas to produce water, what is my equation?
H2
H2,
plus O2
O2. Yeah, someone who isn't Tylee do the rest. Yields.
H2O.
Thanks, not Tylee.
You're welcome.
Balanced?
Find the volume of.
Find the volume of water vapor produced.
No, it's
So
not.
then
Not balanced. So how do I balance it?
You need to put a 2 there and a 2 there. 2 before hydrogen and a 2 before
There
water.
you go. So 4 hydrogen, 2 oxygen, 2 oxygen. What a nice equation that has been up here the entire time.
Yes.
Okay. Next, as Tylee said, do we need to find the molar mass for this actually? No?
Yes.
Let's think about it. Do we?
No.
Anybody else need this?
No, we don't. No, we don't. Because no one made any mistakes. Do we need to find the molar mass of this?
Yes.
Do we need to find the molar mass of the last
No.
video? No, we don't, because look, we're using, as long as it's S2P, we don't need to convert anything. But, well, we'll talk about that in a second. But what should I do? What should I start with?
You gotta hurry up.
I know, I am hurrying up. Okay, what should I start with?
I vote
We don't
you start
know
with the
either.
conversion bar.
Yeah, you have it. So
Conversion bars are so
conversion bar.
fun.
So what's my given?
26.93
26.93 liters of, this is where it's very important,
liters of
H2.
H2.
and we go from liters of H2 at STP to
No.
what?
We're trying to get to what?
We're trying to get to liters of water. What volume of water?
So then go to moles.
Of?
H2.
Okay, keep going.
Then moles over moles.
Moles of H2 to moles of O2. Then
Which is where
moles
you're
of O2 to liters of O2. And that's as far as we need to go.
Okay.
Okay, now here you're gonna find something out that's super lovely about this. How many moles are in a liter at STP? Sorry, it's the other way around. How many liters in a mole at STP? We have to straighten it down.
Oh, I think that it's 22.
22.4 liters is 1 mole. What's our mole ratio?
It would
no.
be 2.
It's 1 to 2. And then once again, 22.4 liters of oxygen is 1 mole of oxygen. We're missing something. So then check out. I need to heart it. I heart chemistry. Okay? And then, but check this out. Look, what's mathematically interesting about this?
You can't.
Yeah, the 22.4 cancels out. So what that means is that when gases are reacting, it's just the mole ratio. So it's going to be super simple because it's just basically the math is just 26.93 liters. What?
Divided by 2.
Divided by 2. So divided by 2.
13.46.
5.
What?
I just got
13.465 what?
I just got 13.48.
It's 5.
13.465 what?
Liters
Of? O2. It's O2.
But aren't
Okay,
we-
now check it out. One last thing before you go. Guess what's going to be possible? Write this down because we'll talk about it more in person. But guess what's going to be possible? Will a gas always be at STP? No. So in order to do this, we need to make sure that our gas is in STP. So for instance, if we're given a gas not in STP, we convert it to STP first, then do this, and then convert it back to the new gas back to the way it was. Do you have questions? It looks like you don't.